Next, we're going to talk about GARCH models. We've already talked about GARCH models, some in the past, so that we could talk about ARCH models. Now we're going to get a little bit more detail, but actually not too much detail. The purpose of this subsection of our notes is just give a brief account of what GARCH models are, how to estimate them, and also to explain that there's a lot of other types of GARCH models out there that we won't talk about here, and I'll give you some references and some names of these GARCH models so that you can explore them further if you are interested. Okay, so the G of GARCH stands for generalize. Our order of our model is M and R. Our model looks like this. Y sub t is equal to sigma t times epsilon sub t, where sigma t squared is this linear combination of the alphas with the y squares. And now the G of GARCH gives us these additional terms. We have a linear combination of beta parameters with corresponding pass variances. Our epsilon t is distributed independent, mean 0, variance 1. Again, expected value of t here is 0. So, the purpose of these GARCH models is to incorporate now past volatilities, as measured by these variance terms that perhaps could affect the present. And the reason why also that these models were introduced was to perhaps look at ways that we can explain the variance in sigma squared sub t, that we can to look at ways that we can explain sigma squared t using a smaller number of parameters than we would otherwise with just an ARCH model. Again, we've talked about model parsimony in the past. We want to use the smallest number of parameters as possible, but still get a good model overall. And so this is the reason behind incorporating these past variances now in this model. When we actually estimate the model, we'll assume normality with the epsilons. Of course, if R is equal to 0, then we have just an ARCH model. Now we can reparameterize this GARCH model and show that it's kind of like just an ARMA model that we've seen obviously previously, but for y sub t squared. So to help see this, let's focus on a GARCH 1-1 model. So we go one time period pass with the y squares, one time period pass with the corresponding sigma squares. And so let's say we have step 1 here. We write out y sub t squared. And what we do is we add and subtract a sigma squared t. Well, what is sigma squared t in terms of our model? Well, we get it right there. Now we have just y sub t squared minus sigma t squared as like a second term. Okay, let's also add and subtract a beta 1 times y sub t minus 1 squared. Then we're going to do some grouping of terms. So this is, let's say, step 2, step 3, step 4 of this process. We have an alpha 1 times yt minus 1 squared. We have a beta 1 times yt minus 1 squared. Let's put these together so that we have alpha 1 plus beta 1 times y sub t minus 1 squared. Also, we have a beta 1 sigma squared sub t minus 1, a beta 1 times y sub t minus 1 squared. Let's put them together by factoring out the beta, a negative beta 1. And so this is what we get here. Notice how we have a yt minus 1 squared, a sigma squared t minus 1, and over here we have still that yt squared minus sigma t squared. So how about we just call this nu sub t? This would be nu sub t minus 1. And now we basically written the model like an AR1 model I'm sorry, like an ARMA 1-1 model, where the nu sub t plays the role of the wt that we've seen before. The y sub t minus the y sub t squared plays the role of this autoregressive term. With this model, there are various constraints on our corresponding parameters. One special model that you will see sometimes discussed is what's called an integrated GARCH or iGARCH model. And what this basically means is this. Imagine you have a GARCH 1-1 model, but now alpha 1 plus beta 1 is now equal to 1. So, excuse me. So based upon what I had written for that ARMA 1-1 representation of our model, look what happens if alpha 1 plus beta 1 is equal to 1. Then I have nothing there. I could bring this y sub t minus 1 over to the left side, as I do there. And now look at this. I can use a 1 minus b there for first differences. And so that's how this gets this name. The I part, the integrated part that we've seen previously for ARIMA, gets put in here with the GARCH. And these models basically are showing that the volatility that we have is persistent, because it can be shown now that the past volatility, these variances, has an effect on all the future ones. I don't know how realistic that really is, to be honest, but some people have found this to be useful. And I guess I just need a good example to see where that truly is needed. Okay. Now, we have y sub t squared in this model. We had this before with the ARCH model. And one, let's say, downside of using ARCH models carries over here to the GARCH models. And what this means is that, let's say, if we think of the y's as returns, like for a stock or a mutual fund, we can think of these y's, either a positive return or a negative return is going to affect sigma squared t exactly the same way. And those who are experts in finance say, well, this might not be realistic. And so because of this, and I'll mention this a little bit later, there have been other versions of these GARCH models developed since the original version that I showed you here that try to account for this, let's say, asymmetric association between the positive and negative returns and sigma squared t. Now, determining the value of R is not necessarily straightforward. What I've seen recommended, and I've tried a little bit in practice myself, is try a number of different models, look at the residuals, see how the residuals look. If they look okay, good, you got a model that works. Otherwise, modify the model. Let's take a look at a short example here associated with this. This goes back to the S&P 500 index values that we saw previously, meaning the ones from 1926 to 1991. And I got this from Pena et al.'s book. And they say, without a GARCH model, the best that you could do is with an ARCH 9, meaning without the G part of the model, you would need to use an ARCH 9 model. So that's a lot of parameters. So let's see what happens. Let's see what they do. We're going to read in the data into R. Here's a plot. Again, we see this volatility, this extra variance appearing at different time points during the series, which suggests now a GARCH model may be appropriate. We can look at now the ACF and PACF for x of t. We'll also do for x of t squared as well. So for x of t, ignore again that first lag, and we really don't have much in terms of significant values. We have maybe one right there. For PACF, we have a few significant values, although notice with respect to the y-axis scale here, and perhaps I should have rescaled it, we're not, relatively speaking, maybe too far above these blue dotted lines or dashed lines. Now in terms of x of t squared, we do have some more significant values here. Okay. Now the author suggests that a moving average 3 or autoregressive 3 model would be appropriate for x of t. Well, why? Notice at lag 3 here, we have probably the largest in absolute value partial autocorrelation, suggesting maybe an autoregressive 3 because of that. Over here, notice again lag 3, maybe a moving average. Of course, this doesn't take into account that we should have tailing off with a corresponding ACF or PACF, but I'm just going to go with what they suggest for an appropriate model. And they focus on an AR3. So let's go ahead and estimate the model. So I estimate the model like usual using the ARIMA function. Here are my corresponding parameter estimates. I put the residuals into y, and then I'm going to look at the ACF and PACF plots for y and y squared. This is what I get. Notice the ACF plot looks pretty good. The PACF plot looks better than what it did before, which is x itself, but we do have some borderline, maybe significant values there. What about for yt squared? Well, yeah, we got some stuff going on in terms of significant values, suggesting that maybe we should take a look at a GARCH model. So here's then the corresponding ARMA 3.0 model for this particular data. Let's now estimate the ARMA model and the GARCH model for the residuals at the same time. The way I can do that is use a function that we've used already with GARCH fit. And the way I estimate this is saying ARMA 3,0. Then for the residual part, GARCH 1,1. And here we go. We look at a summary. Here's the corresponding parameter estimate. So for example, this is beta hat 1 now for our GARCH model. Notice here we have significant parameters, or the parameters are significantly different from 0 here for the GARCH part. But notice for the AR part, oh, non-significant now. And I forgot to mention before they were actually significant before we included the GARCH. We do perhaps some issues with normality. The Jung-Box-Pierce test statistics, those all look really nice. So that's great to see that. We can do a plot of the corresponding information or the corresponding residuals and stuff. What do we get? Maybe a borderline significant one there for the ACF of the residuals. For the squared residuals, they look good. Here's our QQ plot. Here's our little bit of a deviation from normality, unfortunately. So the estimated part of the GARCH model now looks like this. Notice here is my beta hat 1, which we really hadn't seen before. Now, the authors also noticed the with respect to the AR3 part of the model, that maybe, because non-significant, maybe we don't need that AR3 part of the model. So as they suggest, well, what if we drop that part, re-estimate the GARCH model, see what happens? Let's go ahead and do that. So now I just estimate the model with GARCH 1,1. Here, for example, is beta hat 1. They are all the corresponding parameters that we had for the GARCH part are all significant still. Still problems with normality. I should mention that the authors really don't talk about that. But look at the Jung-Box-Pierce tests. Hey, this looks good. We don't have any significant autocorrelation left. So then the model then would become as I showed there. So what could we then do about this normality problem? Obviously I didn't address it. You could look at some transformations of your original data, of course. But I do want to mention, again, that there are many other types of GARCH models out there. And in fact, we could use a different kind of distribution other than normality for the epsilons. And maybe that might work out better. Also, even if we went with this model and still assume normality, what one could do is use what's called a robust estimator for these standard errors. This uses what's called a sandwich estimator. The name sandwich is sometimes, or is associated with the fact that you have your covariance matrix, and you're going to pre and post multiply by two other matrix, well, by another matrix, both pre and post the same matrix. And what that will do is correct your standard errors, which may be incorrect because of this distributional assumption. Sandwich estimators are sometimes taught in a mathematical statistics course. I do know, for example, like the widely used Castello and Berger book briefly do talk about that, where students often see the sandwich estimator, though for the first time, is when they talk about generalized estimating equations to estimate some kind of model where maybe you're observing some information, observing, let's say, multiple values for the same response for the same person, and you want to take into account the correlation that could occur. Sandwich estimators are used there to get still a asymptotically correct estimate of the variance. One could do something like that here, and one could specify that by using a particular option with cond.dist. Now, the authors also suggest using an iGARCH model, because alpha hat plus beta hat, or I should put a 1 there, excuse me, are close to 1. And so one could go ahead and do that. Unfortunately, GARCH fit does not allow you to do that. Instead, I can use the uGARCH fit function to actually estimate it. In my program, I give details about how to do that. It's not too difficult. And this is the actual model that I get. Notice how alpha hat 1 plus beta hat 1 is equal to 1. So that would be another option. Okay, just some quick final comments. Again, first of all, this little subsection is not meant to be comprehensive regarding these GARCH models. There's a lot more details out there that we could go over. In fact, I wouldn't be surprised if there are whole courses on GARCH models at some universities. Now, I do know that for departments of statistics, though, they do not offer courses like this. I wouldn't be surprised if there are courses in like a finance department where more specialized versions of GARCH models could be useful for financial applications. Typically in a time series course in a stat department, you may introduce ARCH models, and sometimes you even will get to GARCH models, but this isn't not necessarily a standard topic that's taught in all departments of statistics for a time series course. Now, as I mentioned before, we're using y squared in our model, we're treating negative returns and positive returns, if y can be thought of as a return, we're treating them the same. Now, there are GARCH models that are set up to allow to not do that. For example, there are what are called eGARCH models that handle that. There are also asymmetric power GARCH models that handle that too. If you're interested, take a closer look at it. But this here concludes our really brief introduction to GARCH models.